just the way the heap's going to work. Okay. So here's where green eggs and ham. Period, line feed, null. That's in there. Well, we're going to have to create another node to point to this. Okay, so we're going to malloc another node. And we have, remember, we have data and we have next. Now, whenever you're creating a node, if you look at the in the malloc textbook, right, you're going to, this guy will always be null. And then here you're going to store your data. I'm not storing the string in here. I'm storing the address of my string. Okay, but don't forget, store another 30, you know, that's another 32 bytes. So how much have I used so far? 9, 10, that's 12, 4, 5, 6, 7. I've used 102 bytes of dynamic RAM so far. Okay, and then the address that goes in here is address 1200. Well, now what do? We have to store tail, right? Tail's got to point to the end here, but before I move tail, I've got to set tail. I've got to set tail pointer next equal to new node, right? This is my new node here. New node, right? New node here. Address. Let's say that's address 20,000. Okay. So now then, that's going to change tail pointer next. Tail is pointing here, and it's going to change its next equal to the address of my new node, which is 20,000 in this case. That's this guy here. Okay. So remember, this guy here gets the address of my string. Then I have to change my tail pointer, right, after. You can't change it before because we'll lose this guy. So then we change this guy, my tail pointer, to point to here. And so tail now has in it address 20,000. Okay. And my node count just bumped up to 2. So now, Johnny, your dynamic RAM is showing 102 bytes. Explain to me why it's 102 bytes. Well, Dr. B, I have 2 nodes in my linked list, and each node takes 32 bytes. That's 64. And then the lengths of my string are blah, 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 blah. Okay. Now, if I want to print this, as I mentioned, right, we're going to have to load, if we do an LDR X0, remember X0 special, put string needs X0 to point to a valid C string, right? So if we load X0 with the address of head, okay, and then we dereference it, so then it's going to have a 10,000 in it, right? But that 10,000 is pointing to this, the first byte of this 16-byte value. So then what do we got to do? I got to dereference it again. Now, X0 has in it 1,000. which is the address of a valid C string. And so now I can do a branch and link to put string to print that particular variable. Now, if I want to print everything, remember, we don't want to ever change head. If I want to print everything, I have another variable called current. And I set current equal to head, right? Now I'm giving you C syntax here. So then instead of loading X0 with head, you load it with current, because this is a temporary pointer. Branch link to put string, and then, and I'm going to just continue this over here. Then we have to increment, and we're going to set current equal to current pointer next, right? Well, how can I do that? Right? So, well, so current, we're going to, so let's see here, assuming that X0 has the address of, well, how are we going to do this? So X0, we're probably going to have to use a different register than X0 for this, for current. So it may be that what we do is we load, say, X1 with current, right? And then we just do the dereferencing here, because I don't want to lose that current address, right? So now X1 has, in this case, X1 is going to have the value of my first node, which was 10,000. Okay, that's this node here. So in order for me to actually jump, I'm going to have to set, I'm going to do an LDR X1. Now, if I did an LDR X1 with X1, what that would do is that would go to 10,000 and then store the 1,000 in there. But that's not what I want. I want this data over here. So somebody tell me, how can I skip those 16 bytes and get to the 17th byte here where the value of next is in this RAM? So instead of it being X1, I need to have an offset, right? Who can tell me how to do that? Who can tell me how to grab that next value that's in there? Just a small change to this line of code. Anybody?
So X1 comma and then the offset of next.
And which is how much? 16 bytes.
I think 102 as we assume.
No, it's not 102. Remember, this is going to be, this will be, this guy here is 32 bytes. And this is contiguous memory. Wait a minute, 32 is a, wait a minute, whoa. 16. A quad is 8 bytes. Wait a minute. So this would actually be more than 32, wouldn't it? This would be 64. I'm off a little bit here. But the premise is the same, right? These are quads. A quad, you know, a word is what? A word is 4 bytes. And a quad is 8. And so we have 2 quads. So we have, that's right, 16 bytes. That's right, 16 bytes. Right, 4 bytes, 8 bytes is a quad. So we have 16 bytes. So actually, I actually was wrong, was right to begin with. Okay, so this is a total of 32 bytes. Well, the first 16 So at address 1000, and let's say that that's hex, or even if that's decimal, at 1016 would be where the value of next is. So I have to add 16 to this. You see? So folks, this is the thing that you've got to get. This is probably the hardest part to understand of all of this, is how do you grab that offset here? Well, X1 is pointing to here, right? This is where X1's pointing. X1's pointing to here. But I don't need these 16 bytes. I need these 16 bytes, which has that 20,000 in it. So we're going to add 16 to this. Then dereference. Well, let's see, actually, do I need to dereference that? No. That's it. So now X1 will be overwritten, which X1 is my current, right? X1 is going to have a 20,000 in it, which is indeed the address of my second node. Here's my first node. Here's my second node here. Okay. Questions? Guys, this, I'm telling you, you need to be on it now. This guy's no joke. He's no joke.
I got a question.
Yes.
So we don't have structs in assembly. I'm just trying to figure out how you get to these, how you even store these.
That's not hard.
Stats.
Yeah, it's actually a lot easier than you might think.
Is it just like a label with two addresses in it?
We don't even do that
Ah.
because we don't need this, right? We don't need to reference that variable. We don't need to reference this variable. Everything we need is in the head and the tail. And then it's just like a chain. We just follow it along. Okay. So let's do this. Let me clear all the drawings. And let's see what we have on our RASM here. Hold on. I don't have my OpenVPN turned on. I don't need OpenVPN. Why did that 192? Oh, it's 168. Now I did a little bit of this last time and I've overwritten this code, I think. Actually, wait a second. I want to remove that. Let's see what this is going to get me. This may completely jack me up now. All right. Okay, so what do we have? Okay, so we have head, we have tail, and I want to make another one called current. It's a quad. Okay, memory used, word, node count, 0. I think that was about everything that we needed. Okay. And then I said info, we'll use data, doesn't matter, info. We're not actually using these variable names, guys, so it doesn't matter. This is just for you, whenever you get ready to do this inside you pull up your old CS3B code for how to do a linked list, right? This way it's the same. Okay. So I don't need this. I really don't need this. I don't think I need these two. We'll comment these out. Because folks, for every variable that we create, that means I gotta take the stuff out of RAM and throw it into memory, or out of the register and put it into memory. So we may or may not use these two. We'll see. We'll see. Okay, so here we had a prompt. Now this one, I'm not reading it from a file. I'm getting it from what somebody typed. And then what did we do? Last time we got it, we did a get string, and we called string copy. Okay, now remember what string copy did. String copy, branch and link to string copy. Remember, string copy is going to request enough RAM for whatever is in whatever's in the keyboard buffer. Okay, and store it into, it's going to malloc, and it's going to return into X0 the address out of the heap where that string got stored. Okay, so conveniently, when I come back out of branch and link to string copy, X0 is going to equal the address of the new string, right? The address of our new string, okay, in the heap. Okay, so that whole thing that we did before, right? Let me go back and this part right here where cat in a hat was extracted out of the keyboard buffer, that's what string copy just did for me. Okay, now if I want that line feed in there, okay, remember, if you're going to make a get line, a file get line, then you're going to need to you're going to need to make sure that you manually add or just continue to save everything, right, to copy over that line feed in there. So to kind of simulate that here, what I would need to do is well, I don't want to mess with this too much. Okay, so just know that if I do a put string here later on, you'll see the reason why whenever I do put string down here. Whenever I do that put string, it's not going to have a carriage return at the end of it. You see, because I was using get string to get the data in. Speaking of which, there's an option on RASM4 where you can also, and you can use any combination multiple times, right? You can also read some data, a line of text from the keyboard, right? Using get string. Well, you're going to have to add that line feed to it. Okay. You're going to add that line feed to it. If you don't, then it's just going to keep putting it on the same line. You see. Okay. All right. So going back to the code that I have here, let's just kind of maximize this out here. Now, most of what I'm doing here, you're probably going to want to create subroutines to do this. But so now then I need to create the new node. Well, I have to know, is this the first? Remember the first thing? Well, the first thing we had to do, we had to create the node. We had to malloc enough RAM for the node. Well, that's here is where that needs to be what? 16 bytes. Okay. Because they're 8-byte addresses, which gives me 8 times 8, 64. Yeah. So 16, I needed 16 bytes for those two struct variables, right? The 2 pointers. One's going to point to the new malloc string that we just previously created from using string copy. And the second half is going to be next. So what do we do here? We set X1 equals the address of my new node. Okay, so that's a single point, that's a single variable. New node will get rewritten over and over and over and over again. Okay, so we're going to store the address of that new 16 bytes of RAM into my new node variable. So now new node's going to have that. New node is going to, that variable is going to have the address of my new node. So now then, I need to set new node info equal to my actual info, right? New node info is going to be, it's going to get to the address of my info, okay? So branch length and string copy, here X0 is going to have that value, right? All right, so let's see, I gotta draw this out, make sure I have this right. So here we've got the keyboard buffer string copy. So what's going to happen is X0 is going to have the address of my new string, which has cat in a hat. Okay, and then we have our keyboard buffer, which had cat in a hat in it. And then we copied that into this new RAM, right? That's what we had to do. So whatever address this was is stored into X0 whenever we come out of string copy. So I'm going to make a pretend that that was address 10,000. Okay. So this did both of these things here. The string copy did all of this. Copy from the buffer. It figured out the size of the keyboard buffer based on the string that was in there, has a null in it, right? And it created the new string, it copied it over, and it's returned the address that Malik gave to it. Okay. Now then, here I need to, I'm about to overwrite. So here I actually lose, I'm going to move into X0, the 16. So here I actually, this is a problem because I don't want to lose. So let's see here, new node equals new node type. That's fine, but we need to keyboard buffer info. So it looks like actually what string copy did was string copy actually, oh, I see what it did. String copy actually did a little bit more for me. String copy actually took that info variable. Remember I said we may not use it. Looks like I did use it. String copy actually stored the address of this new string into my info variable. Well, that's really convenient. That's really convenient. Okay. So it stored it. that address 10,000 got stored into my info variable. Okay, so string copy basically is like this. String copy. It took info, which is a pointer variable. It took info, and then it took the keyboard. Those should be asterisks. And what it did was it created this RAM, copied from here, and stored that stored the address into this pointer variable here. Okay, which is really neat. Now that's my string copy. Okay. All right, so now X0 is freed up to do whatever I need. Well, I need 16 bytes. I've got to create this node. So, and you know what I didn't do though is I didn't. I haven't been updating my RAM count here. Okay, which I would just do manually. So maybe maybe here before I do all this string copying, or even when I come back, because keyboard buff is going to be left untouched. Maybe here I do a you know, I call string length on keyboard buffer to figure out how much RAM I used. You know, I malloc, you know, and then just have like some kind of increment there to increment that local variable to keep track of how much RAM I've malloc. Okay. All right, so now then we're going to grab, we're going to ask malloc for 16 bytes of dynamic RAM, 16 bytes. And we're going to have for the data /info, right, whatever you want to call it. That's going to be 8 bytes. And then my next is going to be 8 bytes. These are quads. Two quads. And so X1 is going to get the value of new node, which wherever new node's being stored in the data segment. And then I'm going to store, because remember X0 at this time, when I come back from malloc, X0 is going to have the address of my new node. And I think we were used 1000 last time, right? So that's the address of this new node is 1000. So X1 is going to get the address of info. And then X1 is going to get the value. Let's see here, info, that's 10,000. Wait a second. X1 gets new node. Okay, so remember new node was another okay. So we're gonna get new node in here, and then we're going to store what's an X0 into the variable new node, which that's where that 1000 is going to go in. So that's the value, which, so now new node is actually a pointer to my new node here, guys. Okay. Now then, here's where I've got to set the data. So I'm going to load into X1. So I'm going to dereference. So what's so address of new node. So now then X1 is going to get a 1000 in it. No. Where am I? I'm here. X1 is equal to new node. That's 1000.
So we'd be getting that allocated bytes, right? What's it, essentially an X0?
Well, so yeah, so these 16 bytes that we got here, the address, the 1000 is coming out of here. X0 equals 1000. And then we're going to, so X1 is going to equal the address of new node. Then we're going to store let's see, let me think for a second here. That's right. So we're going to store 1000 into new node, right? So now the new node equals 1000, which is a pointer to my new node. Okay. So now then I need to use, so now then I've got to store my information here into these bytes down here. I got to get this into here. And so we're going to load, so X1 has 1000 in it. X0 is going to have the address, it's going to have the address of info here, but then we dereference it and we get the 10,000 in it. Okay. So now X0 equals 10,000. Here, X0 equals address of info. Here, X1 equals address of 1000, address of the new node. Okay. So now then what we can do is we want to store the value of X0 into where X1 is pointing. X1 is pointing to here. So there's +0 offset, right? +0 offset, because these first 16 bytes is where the data is. So I don't have to do an offset here. Okay. So this part here is going to set my new node pointer data / info equal to X0, which is my new string, the new string. So that's going to store that 10,000 in here. Okay. All right, now then our so here we're going to put the null pointer into X2, and I'm going to store 0 using X1. X1 still pointing to the beginning of this node, right? X1 still pointing to here, but I need to go 8 bytes. 8? Yeah. I need to go 8 bytes past it, which will get me into here. So this guy here is divided into 0, 1, 2, 3, 4, 5, 6, 7. This is byte 8. So now then I need to get a 0 in there. And I do that with this store. Okay. This guy here is what does that for me. So now that has a null in it, or zeros. Now this was only because this happens no matter what. For every single time you create a new node, whether it's an empty list, whether it's a non-empty list, the act of creating a new node is the same every time. Okay. What's different is management of my head and tail. This part here is the part that's different from here down. So here, if my head is null, then I'm going to set both head and tail equal to the address of my new node. Okay. So here I use x3 equal to head, and I get the value of head. I compare head to null. If it's not equal to null, then I'm going to branch to not equal. So if it's not empty, we're going to skip. But since it is empty in this case, x1 is going to equal the address of my new node. And I'm going to, remember my new node is a double pointer. New node is really this, right? New node is a double pointer. And I'm going to dereference it, the new node, and get this 1000 in this case. We left off here. And then I'm going to get head, and I'm going to store the address of that node into my head. So now head equals the new node, right? So now head has in it, by the way, head should be red because it's in my static, it's a static data member. Head has in here 1000, which is the address of this first node. And I'm going to do the same thing for tail. Tail equals 1000. Points here. Okay, now the else means that the list isn't empty. And you're going to have to figure out the logic that I just mentioned on using tail to append and continue building the links. Okay. Now, linked list guys, you're supposed to be able to, program linked lists before you come to this class. Okay. At least to some minor ability. Okay. This should not be the first time you guys have had to deal with linked lists. Okay. If it is, you got a little bit of catching up to do. All right, so that's basically where this code ends. Okay, and if let's see here. Now, when I'm done, now I commented all this other stuff out. When I'm done, I'm loading my head, and I'm doing the double dereference. Then I'm going to call put string. So if I write this thing out, exit. If I cat in the hat, this thing is going to, using my linked list, is going to display that. But notice there's no carriage return here, right? There's no carriage return. Okay. All right, so with RASM 4, you've got two ways to get data in. And folks, it's a continuous menu, meaning that if I choose option, let's go to RASM 4 here. So I have this menu, folks. So at the very beginning, right? Data structure, heap, memory consumption, 0 bytes. Manually compute that, folks, because you're gonna have to explain it to me when you demo. Number of nodes, 0. view all strings. So right off the bat, we view all strings, it's going to be empty. There's nothing in there. Now, if I type in a B, right, or 2B or just a B, because there's no other secondary options here, that'd be fine. You guys are going to be running the menu, not me. Okay, but you're going to have to demo this live. I may ask you to load the file twice. And what would happen if you loaded it twice? Well, it should be twice as big, right? I might ask you to read from a keyboard 3 times in a row, adding three strings. And then I may ask you to also, so every time you do this, folks, you're appending to the text editor. Okay. So you can either start off, you start off empty, and the user can type in, green egg or a cat in a hat, a cat in a hat, then turn around, and then get the menu again. They type in green eggs and ham. Then the menu displays again. Then they can view all strings. When you view all strings, folks, you should display an index along with the string itself. You're going to regret it if you don't. Okay, because the edit and delete are going to need that. Okay. Right, because how are you going to tell? And the way that delete works, folks, is you're deleting the entire. You've got to delete the. You have to call free. So you first have to load in the address of the new string that was malloc, and then call free. Then you got to load in the address of the node that was used to hold the pointer for that, and then call free on it. Okay. So it's easier if you just give the index number of the linked list. Now there are no arrays in here, guys. None. I mean, I guess technically keyboard buffer could be considered a C string array, but you don't know up front how many pointers are going to be. Okay. So each one of these linked lists let's draw this out. So you're going to have head and tail, and you'll have a linked list that has an address to, see, that's data. Let's just say that's data. Cat in a hat. Next will be the next. By the way, this should also be a blue mark because this is malloc, right? This is a node. So this is a node. You've got head that it's going to point to that one. You've got tail. I'm going to point to that one. And so initially, this thing is null, right? After you've added cat in a hat, then you're going to malloc green eggs and ham, GX, right? I'm just going to blah, 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 blah. That's another. Another node. Okay, we're going to do another one. By the way, carriage return, folks, there are double spaces in there. So this one, actually, if you open up that file, you're going to see that there's double spaces in there. You had to include those. You can't ignore it. Do not truncate that file, which I'll open it up here in a minute and we'll talk about it. But let me just finish kind of going over how these linked lists work. Because now I'm going to go to the third string, right? We have whatever is in here, whatever that string is. Pointer there. This guy here points here. This guy here is pointing to the tail. and the tail has a null in it. So you just keep on doing this as you're building it. So you need to know if I want to, so when I go and I'm doing a traversal to print the entire, the contents of my text editor, right? And it's going to print out this nice, neat cat in the hat, and then there'll be a carriage return, and then there'll be a green eggs and ham. Maybe I think there's like maybe a couple of carriage returns in that text file. These count, folks. These count. And so you'll just traverse using a current, right? You'll set current equal to head because you don't want to modify that guy. And current is the one that's jumping around. See, that current pointer is the one's jumping around and you're calling it. And so you need to know that that was indexed, that's line 0, line 1, just like in Nano, right? We need to see the line numbers. That way, if the user types in 3, delete a string, you give them an index number. Of course, it needs to be a valid index number. And delete the entire string by deallocating the memory. So let's say we want to delete this carriage return or this whatever was here. Okay. Then the address of this dynamic memory needs to be put into X0, and then you call branch and link to free. X0 equals whatever that was. Okay. Then you branch and link to free. That is going to erase this. Okay. Right. Now, this thing here is just you manually printing a count. So the next time, if I were to print, well, before I do that, I also need to set X0 equal to where this node is, right? That's pointing to that. And then I have to call branch link to free from it. And then I have to make sure that my linked list is maintained. All that's in your CS1B text, chapter 16 or 17, I believe it is. Okay. Now, then the next time I print this thing, it'll print index 0, index 1. Okay. This is just a visual aid to help me in referencing this. If I want to edit a string, it's the same thing. Give it the index number and replace the old string with the new. Okay. So that's how Java does immutable strings, right? So if I want to just edit one character in cat in the hat, if I want to just, even if it's, or if I want to make maybe cat in the hats, for example, I got to copy. Well, basically you're going to do a get string. The person will type in whatever it is, cat in the hat, hats, right? That's a new string. That's going to get stored into the address of this new string here goes into this, where this node here is. And then you have to erase the old one. You have to clear the old one up. Right? That guy's gone. This guy here's gone now. That node is now pointing to my new string that we mallocked. Okay. Now string search needs to be, regardless of case, return all strings that match the substring that was given, right? So you're going to have to enter from the keyboard some substring, and then you'll just print off the index number as well. So, maybe it's index 2 has a match along with the string itself, index 15, right? You just print the line number. Now this guy here is pretty tricky too. All right, so let's have a look now. I'm going to clear all this off. Let's have a look at the testing. So here's how the testing is going to go. Test case number 1, you're going to view all strings. Result should be empty. Then you're going to do option 2A. Whatever your input string is going to be given to you during demo time. You're going to type it in. Then you're going to type in 1 to view all strings. And this is what I need to see this. Now this is not part of the string, guys. This is just a visual cue that you create some code that just keeps track of the number of lines that you've printed, the current line count. Okay. And then you follow it up by put stringing the actual string that node points to. Okay, so that's going to go through the entire text editor. Well, there's only one line given to you here. Okay, before we did option 1, there was nothing in there. The result should be empty. There's nothing. Okay, then option 7, you're going to exit the program. You're done. You're done with test case number 1. I'm going to ask you to explain to me what I said earlier. How much RAM did you allocate? By the way, I'm going to want to see whenever you run your code, guys, you're going to have to run it with that val grind so that I can see that you're freeing up your RAM correctly. Okay, which I think I give to you somewhere. I've recorded it somewhere. We'll dig it up later. All right, test case number 2. So you've rerun RASM 4 under val grind, and you're going to read in the text file once. Okay, 2B, you're going to read from the file. That's a static file name. Okay, now I think I had an extra credit option in here to where extra credit of 10 points. Allow the user to enter the file name at runtime to read and save. Okay, but let's understand the basic use cases here. So now then I read in that cat in a hat file, which by the way, if I download this, folks, and I'm going to do this right now, you guys might want to do this with me. This has all kind of Windows special characters in it that you can't see. Okay. And this is one of the things that stumps the students right away. So what I'm going to do right now is I'm going to do a nano -l input.txt. So there's my file. Okay. Now then, if I save this, okay, you'll see that I have 30,508 bytes in this text file. If I run cat input.txt, there it is. There's cat in a hat. I may or may not be able to get all of it. That's actually kind of impressed here that I've been able to go this far. So cat in a hat. Look, there's a carriage return, guys. Carriage return. Now look, because I can click over here doesn't mean anything. There's a carriage return or line feed, line feed, line feed, line feed right there. So the second test is when you save the file. Okay, so you're going to read in input.txt. You're going to read it in, then you're going to save it immediately. Basically, you made no changes. You made 0 changes to that input.txt file. So when I save it as output.txt, you got to save it from what's in your, from your linked list. Okay. And so when you do this, you're going to run right in front of me after you've exited the program. There's an instruction called diff. Now what diff will do is it will go character by character, byte by byte, and do a comparison between 2 files. So if I take in, let's say I copy input.txt into output.txt, of course, that's going to be an exact match, right? 30,508. If I run a diff, and what was the other flag? Diff -s against the output.txt, it's going to tell me that they are identical. If they're not identical, folks, you have failed that particular test has failed. Okay. And most likely what it is that you have saved extra characters to the output file that don't belong. There should be no change there, right? You read the file in, you have the option of appending things to it and then saving. You have the option of editing the thing and deleting things. But the second test case is very simple. You're proving to me that your logic is sound and your program can read in the file, output it, and it is going to be identical to its original value. Okay. Test case number 3. Okay, you're going to read in the file, cat in the hat again. Okay, then you're going to append this text, segmentation fault, and that is a cruel, yes, it is cruel. It's cruel because you're going to get so many seg faults on this assignment that you're going to be sick of it. Okay, then you're going to view all strings. So the result should be the original file plus this one new string above. Then I'm going to have you do a search. And I need to add an edit. I don't see where I'm having you guys do an edit. So you're going to search with the intention of deleting one of those lines. And I'm going to give you the string, the substring to search for. Okay. So if I were to search, so there's 3 lines on here with tomorrow, but there's also one that's in there, it's lowercase, right? So your search has to be case insensitive. So I don't know what line numbers these are. I think grep actually would allow me to list the line number. Let's see here. Let me do a quick look. Man with grep. The -n. All right. So if I run this with the -n flag, at line 965. So this is very similar. Oh, this is actually identical to what you should be doing. Your program should be doing. Now it depends if you're going to use 0-based indexing or 1-based indexing. I don't, actually I think I do care because I told you here that this should be index 0. You're going to want to use 0-based indexing, guys. All right, so that is test case 3, and you'll delete that line number. You'll view all strings to show that it is, you'll view all strings to show that that particular line was deleted. And this one's going to be option 5, which should be edit, right? String search. So this one here, I need to modify this. String search with the intention of editing one of those lines. And then here, I'm going to tell you to input edit, or basically do the edit given to you at runtime. And verify that edit works. There we go. Okay. All right, folks. So that's pretty gnarly. Now, I actually need to take a quick break. I'll be right back. I need a bathroom break just like everybody else does. So I'll be back, guys, and give me about 10 minutes. I'll be right back. 5-10 minutes. Okay, guys, it looks like we have what, about 35, 40 minutes left? Is that right? Am I looking at this right, class? It's 1:08. I've got you guys to 1:50. Anybody still here?
Yeah, I'm still.
Yeah.
Yeah, something like that.
All right. Okay, so so this thing is due, folks. We're going to have to demo. I can't delay it. It's due December 5th, which is in 4 days. So this is what we got to work on. Now, I will say this, is that looking at our schedule, let's see here. The 6th. You know what, I could probably move this to the 8th, but that would be it. I can move it to the 8th. Let me do that. Give you guys a little bit longer to deal with it, but we're still going to have some things. We've still got more material to cover, as always. It's like you never run out of material to cover. But that's a little bit better description of RASM 4. Okay. All right, so for this time, you'll be creating a menu-driven program that serves as a text editor and saving the result to a text file. You must be able to enter new strings manually and or via a file, input.txt. All additions are additive. In essence, I can call 2B 5 times and 5 copies of the text file will be stored in the data structure. Linked list of strings. Use the enclosed file for possible input. Do not load automatically, only via the menu. Right? I may not choose to load the data from the file. Okay. If you read in the input and then immediately save the output, okay, should be identical in every way. All right, so those are our test cases. Extra credit, 10 points, is allow the user to enter the name of the file for reading it, for input and output, for reading and saving. Okay, let me edit that to make it read better. So basically allow the user to enter the file name for reading and writing. Okay. These are 2 different files, folks. Now, because what you could do then basically is, yeah, you could write your data and then open it back up if you wanted. Now, I've actually had students in the past, I found like a really large text file. So let's see here. I don't know if that's still the same. Is that with Scarlett O'Hara and all this? Yeah. So this guy here is pretty big, right? So you could actually read in any text file with this and, use it as a text editor, right? All right. Now, what do we have left? We'll have a quiz. Quiz 8 is about, not quiz 8, quiz 7 is about reading and writing. You do have an additional program here. Now, Lab 22 is meant to help you with this guy here. Exam 3. So your exam 3, RASM 5, it's published. You can look at it now. You have all this time to work on it. Now, what it's going to be doing is, so for the actual exam day, guys, you're going to demo running this for me. Now, this is not a group project. This is individual. And you're basically going to create a menu where this is written in C++ or C, whatever you want, C or C++. And you're going to create your own input.txt file. I don't care how you do it, right? But you got to have 200,000 random integers in that thing. People ask me, well, what should the range be? I would say make it interesting. I don't know, 0 to 1,000, 0 to 5,000, 10,000. Make it interesting, okay? Don't make it like only 10 different numbers. I mean, that's, that's not very interesting. So what you're going to do is the way this works is first you load the input file, the integers, okay? Again, this is C++ or C. And then you're going to call the sort using C bubble sort algorithm, okay? And later we'll talk, or C bubble sort algorithm. Now what you've got to do is, and I believe I actually have the code for this assembly version of bubble sort. So you got to make sure that these two algorithms are identical. Now this one is going to be an external function that you create that you're going to pass a pointer, just like you are to this guy here. You're going to pass a pointer to an array, and then you're also got to say an x0, and then an x1 you pass, the number of elements, just like you would with the bubble sort algorithm in C++ or C. And then you're going to compare how much time it takes for each of these to complete the sort. Now remember, folks, after you sort, now look, I'm not asking you to print anywhere in here, okay? Now you do need to verify that it worked, okay, by spot checking the output file. Okay, so every time you sort, you need to save the array to its respective file, C output text or assembly output text, okay? So that I can verify that your sorting algorithm works, right? So if you read in the input file and then immediately save, the output should be identical to the file. What's this one here? That doesn't make sense. Ignore that. Okay, so here is the code that I need you to use, right? Everybody needs to use the identical. So also make this an external function. Make this an external C or C++ function. That way it doesn't have any advantage over the assembly version. Okay, now what you're going to do is when you compile RASM5, by the way, folks, this is meant to be a pretty easy problem. It's very easy, okay, compared to RASM4. So here I've assembled the bubble sort. So this is the assembly version of bubble sort. Okay. Now then, when I go to compile, okay, for those of you that don't know, the -C flag says compile without linking. Okay. Then we're going to assemble the bubble sort, creating a .o file. Now then, we're going to complete the linking of RASM5. I mean, I guess you could call it RASM5.exe here. That's probably better, better. And then this way, it will grab the assembly version of your bubble sort along with the original code that you had here. And then for extra credit of 20 points, now this applies towards your exam grades, add the insertion sort function to the menu set. Okay. So here you would just you're doubling your options here. Okay. And we're going to keep track of how long it takes to sort using the different languages. And you're going to be surprised. You're going to be surprised how much faster these guys are. Okay. And this will be, as far as the due date for this, whatever, it's whatever the due date's going to be for our, whatever whatever our final day is. Okay. So half of your time on the final will be spent answering the final exam. The other half of your time, class, is going to be demoing RASM 5. If you want to demo RASM 5 prior to the final exam day, you can, and then you have the entire exam period to complete exam 3 lecture. But exam 3 RASM 5 is due at the beginning of class that day. You're not going to have till midnight and all that jazz. So that's why I'm opening this up now. So the lab for, and we can talk more about this as time gets closer and closer, but this lab here, lab 22, create an input text file that has these values in it. And then what I want you to do is after you load it into RAM, okay, now I don't tell you whether you have to make this dynamic RAM, but you should. You're not going to be able to statically, let's see here, that 200,000 integers, by the way, guys, on that C++ program, that's going to need to be a dynamic array in C++. I don't know that you can create different arrays, more than one or two of those. You'll run out of memory, static RAM. So you're going to want to do that with dynamic RAM. But this one doesn't matter. But I do need you to show me, give me a memory dump of the array and only the array. Okay, so part of this, guys, is you proven to me that you know how to grab just that data. I don't want to see nothing else. I don't want to see extra bytes. You need to show me that you can navigate through using GDB and show just these 1, 2, 3, 4, 5. And these are integers, right? These are 4-byte values. So 1, 2, 3, 4, 5, those 20 bytes. Okay. So folks, today there was quite a bit, right? We actually have talked about quite a bit. And let's see. I'm going to let that settle in. Quiz 7. Let me stop sharing for a moment. I'm going to have to modify quiz 7 because it's all about, here, I mean, I can show it to you. So quiz 7 is basically, now look at this. This is awful because Canvas and tables don't work very well together. But I'm going to ask you, to do some matching here. Tell me what needs to go in which registers for opening a file, for reading a file. So basically that website that Alex put on there, the code that we wrote, that identified what goes into each of these registers is what you need to be able to give me. Okay, match the standard handle descriptions to their corresponding code. We talked about that, what 0, 1, and 2. What are the basic syscalls in ARM Linux? See, I got to change this now because we have what? A read at. Which ones return anything in X0 is the way this one will read. So we've got to explore these. You got to explore these. So I'm not going to publish this yet because I have to go in and edit it myself. So we'll have this quiz. And then when we come back to class on Tuesday, we're going to get into the last topic, which is the general purpose input-output assignment. And I can turn these on. Now, these folks are there was a, let's see here, GPIO. Okay. So if you guys do lab 23, and there's not a whole lot of time, but lab 23 is going to require you guys to buy a couple of wires, or your pies may have already come. Some of them may have already come with some. But Lab 23 is an opportunity for you to grab 20 points added to your exams grade, not assignments, but your exams grade. So if you want some extra, some extra buffer, if you didn't do so well on your exams, okay. So you will need to demo your functioning solution along with uploading your code. Demo must be completed before the final exam. And let's take a look at this. So basically what you're going to do is you're going to hardwire you're going to hook up an LED through a small breadboard, and you're going to control the brightness of the LED and how fast it flashes. Through doing some work. Right? Let me show you what it's going to look like. Again, this is optional. You don't have to do this. So here is another 10 points. So this one is pulse width modulation. So there's a total of 30 extra points that you can have added to your exam grades. And where's my video? Now, folks, this video, he does it using Python. You're not allowed to use Python. You got to write this in assembly. And we'll talk more about this later. But basically, here's an example. Let's see here. Where are we?
No, how we connect the pin used to trigger them.
Okay, that's a different component. There's one on here that shows an LED. Programming, chapter 11, chapter 12, 23, GPIO, TGZ, labs. Oh, here we are, down here, these two videos. So this one is basically what.
Hey, you know what's better than $5,000 PC?
Nope, we don't want to know what's better than $5,000 PC. That's actually a good guy. I like that guy. So basically what you're going to do is hook, this guy here is just an extender board. You don't have to have this, okay? But this is going to connect to your Pi, and you're going to control this LED from your Raspberry Pi, the general purpose input output pins. And the trick is these pins, these things are going to be way different, right? It's going to be different because this is a 32-bit system here. So you're going to be working with these pins and controlling that LED, okay? Which we'll get into the last week of class, right? But you won't have time if you seriously want to try this, guys. And even if you try it and you can't get it to work all the way, I'll give you something. But students really seem to enjoy this project. But remember, it has to be done in assembly, not Python. And it's a way for you to get to know your Pi. Okay. So these are this is what we have left in the class to go over. And let's see here, what was lab 25? Yeah, we'll do lab 25. So lab 25 is just getting you ready for RASM 5. I mean, I'll publish it even though it's late. Let me just edit the thing here so you can see it. So this is going to be a good build up to your exam 3 lab, where in C++, you're going to call the length function of C++, which is you know, which is a part of the C++ library. And then you're going to call the string length function that you wrote in assembly and verify that the results of these two things are the same, which that's going to be a pretty neat exercise, but we can't do this until we wrap up the thing with our RASM4. Okay. And let's see here. Exam 3 lecture, exam 3 study guide. Turn that on. Let's see here. I don't have quiz 8 is over the GPIO, general purpose IO pins. So we'll cover that. Remember these two here, they're showing 0 points because these are extra credits. All right, so we're here, folks. We're at the end. All right, so the alligator that's closest to the boat is the lab that's due tonight. File IO reading. Okay. So I'm going to turn you guys over. We got about 20 more minutes. We're technically in your lab time now. So let's do this. Let me go ahead and take attendance, and then I will leave you guys to your own for what you're going to do with the remainder of your time. Okay. So I need you guys to in chat. Once I call off your name, say that you're here. And remember, folks, if I call you off a couple of times, if you don't respond, even if you're in the room, it counts as an absent because you've got to be paying attention. You can't just be off working or delivering pizza or something. Okay. All right, Jared, Daniel, and Chase. Is Daniel? Okay, perfect. Anthony, Angela, and Jonathan. Is Jonathan? Perfect. Duncan, Brandon, and Eric. Duncan's not here. All right, Gregory, Alex, and Yassine. Alex. Okay, Alex. Okay, Jordan, Benjamin, and Johnny. Okay, one last time. Duncan Hutchinson and Alexander Constal. Okay. All right, folks, that's it for me today. Does anybody have any questions other than when's the assignment's going to be graded and all that? Aside from that, for the content that's due tonight or RASM4, what questions does anybody have?
I think you need to publish the GPIO module because I don't see it on Canvas.
Let's see. Oh, yep, you're right. How about now?
Yeah, I see it now.
Okay. All right, guys, I'm going to ghost out and I'll see you on Tuesday or Monday. See you on Monday. Take care.